All right, so carrying on with our example. This is the simplified integral form of the equation. What we need to do now is take our velocity profile that we solved for up in the upper left and plug that in, and now get an ODE in terms of delta. Before I start plugging in, there's a bit of a complication here. What about this shear stress? We don't really have a readily available expression for shear stress. I know U, I can just plug in U, but we need to get shear stress in terms of velocity. So what I would do first is I'm going to go back and try to derive an expression for the shear stress that's in terms of the assumed velocity profile that we've made. So to do that, let's go back. Let's say tau s is equal to mu partial u with respect to y, evaluated at y equals 0. That's our shear stress at the surface. So in order for this to be represented, we have to make sure that our shear stress matches the assumed velocity profile. Like if you plug in some other approximation for shear stress, you're going to be inconsistent. It's wrong. So you want to make sure the shear stress matches the velocity profile. So let's take our u and plug it into the shear stress and see what we get out of that. So we would get this is equal to mu times partial with respect to y of u infinity 2 y over delta minus y over delta squared. All of that's evaluated at y equals 0. That then equals, let's see. Yeah, so I'm taking the derivative with respect to y. That gives me mu times u infinity is a constant. That comes out. We have 2 over delta m minus 2y over delta m squared. Still, all of that evaluated at y equals 0. And then last simplification here would just be it's equal to 2 mu u infinity over delta m. So that's my shear stress, right? That equation is consistent with my assumed velocity profile. If you did a linear assumption, it would be different. So you have to go through this step. Now we have this expression for shear stress in terms of u, or u infinity, I guess, is in terms of delta m. We can then plug that into our equation. OK, so now we're kind of in a position to actually do this. So plugging this stuff in, I'm going to plug in my velocity profile. Starts to get a little bit messy, but we'll just walk through it so you can see what happens. So d dx of the integral from y equals 0 to delta m of the quantity, let's see, 2 parentheses here. So that would be 2y over delta m minus y over delta m squared. So the first thing was u squared, right? U squared up here. So this is u. So this is going to be u squared here. OK, so that's u squared. And then that's all times u infinity squared minus the quantity 2y over delta m minus y over delta m squared. That's u times u infinity squared. So then get some of this stuff out of the way. Sorry. That's the close. Let's see, that goes there. So this is then dy. This is integral with respect to y. And then that's all equal to minus 2 mu u infinity over rho delta m. See, did I get all that? So we have the derivative. We have the integral with respect to y. So this goes with this one, dy. I think we're OK. So you see that all we've done is just plugged in u. So where did that u infinity come from? My assumed velocity profile has u infinity. Yeah, so u infinity squared. So we're OK, I think. Should just be subbing it in, but keeping track of it. All right, so now we have this integral. We have expression that has y and some constants in it. we have this integral, so we can just integrate this, right? It's pretty easy to integrate that with respect to y. To do that, I guess maybe we could expand it out, but how do we do this? Yep, let's just go through the steps. And all right, so we're going to expand it out and integrate each term. So then we get d dx of, having integrated it would be this whole thing. So it would be 4/3 y cubed over delta m squared minus 4 over 4 y to the 4th delta m cubed plus 1 over 5 y to the 5th delta m to the 4th minus 2 over 2 y squared over delta m plus 1/3 y cubed over delta m squared. So then this whole thing from the start to that point would be evaluated from 0 to delta m. Then that's times u infinity squared. And that's all equal to the right-hand side, which was minus 2 mu u infinity over rho delta m. So what I did was factor this stuff out. So you have like y squared, y to the 4th. You have that sort of factored out term here. And then the integral of those become y cubed, y 4th, y 5th, and so on. So now we just need to evaluate this from delta m to 0. And then take the derivative of that. So doing that, I guess we have what? This becomes, hopefully going to run out of room here, so dx of evaluating this integral. So it becomes 4/3 minus 4/4 plus 1/5 minus 2/2 plus 1/3 times delta m times u infinity squared. Okay, and then on the right-hand side, it's still 2 mu u infinity over rho delta m. Okay, we can simplify that down. The common denominator here would be, this is 1, so this common denominator would be 15, I think. So you end up with something over 15. And that is dx of minus 2/15 delta m u infinity squared equals minus 2 mu u infinity over delta m, rho delta m. OK. So we have an ODE, finally. Some constants. This is an ODE in x. Delta m is our variable. Kind of curious, right? But we went through this whole process, integrate everything out, and then we end up with this ODE. This ODE now tells us, if we solve this ODE, it will tell us, as a function of position x, what my boundary layer thickness is. And that's what we care about.